Hello, myself Chetansing Rajput, and today we're going to discuss about golden ratio. The geometry of golden ratio, which is based upon a special right triangle. This right triangle having its catheti in the ratio 1:2. Look at the sides of this triangle, 1, 2 and root 5. These side lines provide the exact fractional expression of golden ratio, which is nothing but the solution to the quadratic equation, this x square minus x minus 1 equals 0. And not just sides, even the angles of this right triangle. The angles of this triangle are also the precise expression of golden ratio. Like this acute angle here against the longer catheti. This angle measures 63.435 so on in degrees, and this acute angle here, this angle measures 26.565 so on in degrees. Look at these figures, these measures of angles in degrees. These values are also the precise expression of golden ratio. Like this angle, 63.435 degrees. This is precisely equal to twice the arc tangent of the inverse of golden ratio. Alright? And this angle here, this angle precisely equals twice the arc tangent of the inverse of phi cube. Alright? Now look at all these three angles. This is right angle, of course. Look at the angles against the sides which are in numerator in this fractional expression. The angles against smaller catheti and angle against hypotenuse, 90 degree and this 26 point something degrees. These two angles add up to a very peculiar value, which is equal to 116.565 degrees. 90 degree plus this smaller acute angle, they add up to this value, and this value is precisely equal to twice the arc tangent of golden ratio. Now look at these two figures. The angle against 1 and root 5 sides, they add up to arc tangent of golden ratio, twice of that. And the angle against the denominator side, the longer catheti, that angle is twice the arc tangent of inverse of golden ratio. And these two angles, twice the arc tangent of inverse golden ratio and twice the arc tangent of golden ratio. These two angles are precisely the angles of golden rhombus. And not just golden rhombus, these two angles are closely associated with all those geometrical figures which are concerned with golden ratio. Like these two angles are the dihedral angles of regular dodecahedron, great dodecahedron, small stellated dodecahedron, etc. Moreover, not just sides and not just angles, every geometric aspect of this 1, 2, root 5 triangle, every geometric aspect of this special right triangle is simply the purest expression of golden ratio. Like this. Suppose this point here in this triangle, this point I, it is the in-center of this triangle, which is denoted by x1. Kimberlin Center Encyclopedia, it is denoted by x1 here. Now, if we draw an in-circle with center at point x1, this in-circle of the triangle touches the sides of triangle at point P, Q and R. These P, Q, R are the in-touch points or the touch point of the in-circle. These 3 points P, Q, R, these are also the vertices of Gergon triangle, the Gergon triangle of this reference triangle ABC. Now these 3 points P, Q, R divide the side lengths of the triangle in a very peculiar manner. Like this point Q, divide the hypotenuse AC in a very precise manner like this. This distance QC here is precisely equal to golden ratio, and this distance AQ here is precisely equal to inverse of golden ratio. Golden ratio and inverse of golden ratio, they add up to square root of 5. Similarly, this length here RC, this is equal to 5, and this length here BR, this is equal to in radius of the triangle, which is 1 upon 5 square. Again, this PB is also 1 upon 5 square, and this distance AP, this is inverse of 5. And not just in circle, even the X circles of the triangle, like this is one X circle, this is second X circle, and this is third X circle. Even the touch point of the X circles, suppose L, M and N. These are the touch points of 3 X circles of this 1 to root 5 triangle. Touch point of X circle means these are also the vertices of Nagel triangle. These points L, M, N also divide the triangle sides in terms of golden ratio, but this time exactly in inverse manner. Like now this distance AM is equal to 5 and MC is inverse of golden ratio. This distance here and C, this is equal to 1 upon 5 square. This distance BN, this is equal to golden ratio. This distance AL, this is 1 upon 5 square, and this is 1 upon 5. It can be easily derived because the Nagel triangle vertices are the perimeter splitters of the triangle. Hence, the golden ratio is found in every aspect of this 1 to root 5 triangle. It is present in the side lengths, it is present in the angles. Golden ratio is present in the Gergon and Nagel triangle of this 1 to root 5 triangle. It is present in the Knopf's point, it is present in the Gergon line, it is present in the N circle and the X circle, in red D, X red D. Every geometric aspect of 1 to root 5 triangle is full of golden ratio. More importantly, this triangle 1 to root 5 is found to be closely related to a regular pentagon that we'll see in the next session of this video. I request the viewers to kindly visit the paper link. All these things have been published in a research paper, and the paper link is provided in video description. Thank you. Alright, and welcome back. In this part of video, we're going to discuss the close association between this 1 to root 5 triangle and the regular pentagon. Regular pentagon whose geometry is full of golden ratio. Okay, we'll see this thing in 2 parts. In first part, we will see how we can construct a regular pentagon with help of this triangle 1 to root 5 right triangle, and in second part we will see how this length proportion 1, 2 and root 5, these length proportions are present in regular pentagon. So let us see the first part. Consider the reference triangle ABC. It's a right triangle with its catheti in proportion 1 has to 2. In center of the triangle is at point I, and this in radius ID is perpendicular to the cathetus BC. Now let's draw a circle with center at vertex C and radius equal to cathetus BC. A circle like this. I'm not very good at drawing circle, but consider this circle with center at vertex C and radius which is equal to triangle side BC. Okay, a circle like this. Now consider this in radius ID which is perpendicular to side BC. Let us extend this in radius like this. I extend the in radius ID to intercept the circle at point P and point Q. Okay, this chord PQ, which is nothing but ID produced, or the chord PQ is perpendicular to triangle side BC and it is passing through in center I. In this case, this chord PQ provides the side of a regular pentagon which can be inscribed in this circle. I repeat, this chord PQ provides the side of a regular pentagon which can be inscribed in this circle, like this. Okay, I repeat the whole thing. Triangle ABC is a right triangle with its catheti in proportion 1:2. In radius ID is perpendicular to this catheter BC. We draw a circle with center at point C and radius equal to BC. Then we extend this in radius ID to intercept the circle at P and Q. Then this chord PQ provided the side of regular pentagon which can be inscribed in this circle. Let us name the vertices of the pentagon: P, Q, R, S and T. Okay. Now, if the side of the triangle BC, which is equal to 2 here, is the circumradius of this pentagon, in that case, the side of the pentagon is equal to 4 times sine 36. Similarly, diagonal of the pentagon, which is in golden proportion with the side, equals 4 times cos 18. Okay, apothem or in radius of the pentagon is precisely equal to golden ratio, and height of this pentagon is equal to √5 times golden ratio. Alright, consider these angles: 36 degree or 18 degree or 54 degree or 72 degree or even 108 degree. These angles are closely associated with golden ratio because these are the angles which are present in regular pentagon as well as in golden ratio triangle. Okay, so this triangle 1 to √5 provides a novel method for constructing a regular pentagon. Also, let us see the second part now. These triangle lengths, these side lengths 1, 2 and √5, these length proportions are also observed in the geometry of a regular pentagon. Let us see how. Consider diagonals of this pentagon. Diagonals like this. Diagonal TQ and diagonal PR. These two diagonals intercept the circumradius BC at point X. Okay, and I would like to mention this point X where the diagonals of regular pentagon intercept the circumradius. This point X cuts the circumradius in golden ratio. In other words, BC upon BX, this is equal to BX upon CX, and that precisely equals golden ratio. Okay, now more importantly, consider these 2 points, X and D. X is the point where diagonals of pentagon intercept circumradius BC, and D is the point where the side of pentagon PQ intercepts the circumradius BC. These 2 points, D and X, they precisely divide the circumradius in the ratio 1 √5 and 2. This length here, this length is equal to in radius of the reference triangle. This is 1/5 square. This length here, dx, this is √5/5 square, and this length here, cx, this is 2/5 square. Hence, BD has to DX has to CX is precisely 1 has to root 5 has to 2. In other words, the diagonals of regular pentagon and the side of regular pentagon intercept the circumradius at two such points which cut the circumradius in the proportion 1 has to root 5 has to 2. Okay. Another important thing. Consider this length BX. Okay. This length BX is precisely equal to 2 upon golden ratio. Okay. And this length 2 upon golden ratio. This length provides side of a regular decagon. Side of a regular decagon. This length or this length 2 upon golden ratio. This is side of a golden decagon that can be inscribed in same circle. Okay. Now, more important thing. Here, the circumradius of this pentagon is equal to 2, which is longer catheti of our reference triangle, and apotheme of this pentagon, which is equal to golden ratio. Okay. Consider the circumcircle of this pentagon and the incircle of this pentagon. The area enclosed between these two circles. The area enclosed between these two circles is precisely equal to root 5 into pi upon golden ratio. Okay. The circumradius of this regular pentagon is equal to side BC of our reference triangle, which is equal to 2. And apotheme or in radius of this regular pentagon is golden ratio. And the area enclosed between circumcircle and incircle of this pentagon is equal to root 5. This can be easily calculated from this formula. The area enclosed between circumcircle and incircle is equal to pi side square upon 4. Alright, now see this formula. It's an interesting formula because this pi is a transcendental number. Okay, and golden ratio of phi, it's an algebraic number. It is solution to the quadratic equation x square minus x minus 1 equals 0, and it is the most irrational number of all irrational numbers. Although it's a transcendental number and it's an algebraic number, this triangle, this regular pentagon enables us to derive a precise geometric relationship or precise correlationship between pi and phi. Okay, and not just pentagon, this triangle and its several other features like incircle of this triangle, that also enables us to get the precise geometric correlation between pi and phi, which is firmly premised upon classical geometric principles. Okay, so all these things are described in detail in my paper, and the paper link is provided in video description. So I request you to kindly visit the paper link. Thank you so much. Hello. So far we have seen how the special right triangle, the 1 to root 5 triangle, is closely associated with golden ratio. In this part, I will elaborate some other golden features of this triangle, like the precise measurements, precise calculations show that in this 1 to root 5 triangle, every feature, every aspects, each and every calculation of this triangle is associated with golden ratio, like semi-perimeter of this triangle. Semi-perimeter of 1 to root 5 triangle precisely equals the square of golden ratio. Okay. The in radius of this triangle is precisely inverse the square of golden ratio. And not just in radius, all three x rad d of this 1 to root 5 triangle, each of the x radius is the precise expression of golden ratio. Like the x radius opposite to right triangle R1 is equal to square of golden ratio. Another x radius is precisely equal to golden ratio, and the third x radius is inverse of golden ratio. Every calculation excuse me, every calculation, every figure, semi-perimeter, in rad d, x rad d, everything is precise expression of golden ratio. Even the trilinear coordinates or barycentric coordinates of different triangle centers of this triangle, like Jergon point or Nagel point, Mittenpunkt, every triangle center, its trilinear coordinates, its barycentric coordinates can be precisely expressed in terms of golden ratio. I also want to mention an interesting thing. If we incorporate in circle, in this 1 to root 5 triangle, we can observe a precise ratio between the area of this triangle and its incircle. The ratio is like this: the area of 1 to root 5 triangle upon the area of its incircle. This ratio is precisely equal to 5 raised to 4 upon pi. The area of this 1 to root 5 triangle upon the area of its incircle. With incorporation of incircle, naturally pi enters into the picture, and this triangle is full of golden ratio. Hence, if we calculate this ratio, area of this triangle upon area of its incircle, we get this interesting equation. See the beauty of this equation. Phi here is an algebraic number. It is solution to a polynomial equation, and pi is a transcendental number. But this triangle enables us to get the precise geometric ratio between these two numbers, and this is precise up to infinite decimal places. The precise pi-phi correlation. We will see the details of this pi-phi correlation based upon this triangle in subsequent parts of the video. So keep watching the video. Here, let us see some other golden aspects of this 1 to root 5 triangle. Like, see here. Here are, this green are the bisectors, angle bisectors of three triangles of this 1 to root 5 triangle. And I would like to mention the angles between these three angle bisectors. The angles between three angles bisector, they meet here at the incenter I. See the angles between them, like this angle here, the angle between two bisectors. This angle is precisely equal to arctangent of pi cube. Okay. Angle between these two angle bisectors. This angle here precisely equal to this angle, arctangent of golden ratio. And this angle, the angle between these two angle bisectors, this angle here is arctangent of 1. This is equal to 45 degrees. Tan inverse of 1, phi and phi cube. Similarly, the angle between each angle bisector and the opposite side. I repeat, the angle between each angle bisector and the opposite side, like this angle, and this angle. Interestingly, this angle here is arctangent of phi cube. Again, this angle here, the angle between longer catheti and this angle bisector, it can be expressed in terms of golden ratio. It is precisely equal to arctangent of golden ratio. And this angle here, angle bisector of right triangle and the hypotenuse, this angle here is precisely arctangent of 3. Such an interesting triangle. Similarly, in this part, these are the in red D perpendicular to 3 triangle sides. This is I, or say x1, the in center, and these 3 in red D are perpendicular to 3 triangle sides. Okay, just see the angle between 3 in red D which are perpendicular to triangle side. This angle here, this angle is precisely equal to twice the arctangent of phi cube, twice the arctangent of cube of golden ratio. Okay, similarly, this angle here between these two in red, this angle is twice the arctangent of golden ratio. Okay, and this triangle here between these two in red D, this is twice the arctangent of 45 degree. Sorry, twice the arctangent of 1, means it's a right triangle, obviously. So every angle in this triangle can be expressed in terms of golden ratio. See, another interesting thing here. See this 3 in red D perpendicular to 3 triangle sides, and such 3 in red D divide this triangle area in specific manner. Area of these 3 portions can also be expressed in terms of golden ratio, like area of this quadrilateral here, it is precisely equal to 1 upon golden ratio. This is 1 upon phi. Okay, area of this quadrilateral here, this is also precisely equal to 1 upon cube of golden ratio. Okay, and area of this square, the in radius is 1 upon phi square, hence area of this square is 4th power of golden ratio, inverse of it, 1 upon phi raised to 4. And these 3 areas of these 3 portions, 1 upon phi cube, 1 upon phi raised to 4, and 1 upon phi, they add up to area of this whole triangle, that is 1. Okay, so the entire geometry of this 1 to root 5 triangle is full of golden ratio. Now, before ending this session, I want to mention a couple of interesting things about this 1 to root 5 triangle. You guys must have heard about the Fibonacci Pythagorean triples. You must have heard about the Fibonacci sequence 1, 1, 2, 3, 5, 8, 13 and so on. We can generate Pythagorean triples using the Fibonacci sequence. Like the Fibonacci sequence is like 1, 1, 2, 3, 5, 8, 13, 21, 34, 55 and so on. We can generate a sequence of Pythagorean triples using this Fibonacci series. And is such series of Fibonacci Pythagorean triple, we can generate a Pythagorean triple with alternate Fibonacci number as their hypotenuse, like 5, 13, 34, 89 and so on. We can generate Pythagorean triples with alternate Fibonacci numbers as the hypotenuse, like first such triple is 3, 4, 5. Okay, another such triple is 5, 12, 13. Okay, another such Pythagorean triple is 16, 30, 34. Next such triple will be 39, 80, 89. Okay. Look at these numbers. These are Pythagorean triples, and these number 5, 13, 34, 89 and so on. These are alternate Fibonacci numbers, and we can generate such infinite numbers of Pythagorean triples using the same method. Infinite number of Pythagorean triple. And the most interesting thing, as such series of Pythagorean triple advances, these triples approach to attain the ratio of 1 to root 5 triangle. Okay, as such series of Fibonacci Pythagorean triple advances, such triple attains the ratio of 1 to root 5. Means the two catheti of this triple approach to attain the ratio 1 has to 2. You getting my point? Just like as the Fibonacci sequence advances, the two consecutive number approach to attain the ratio between them, which is equal to golden ratio. Okay, as the Fibonacci sequence advances, the two consecutive Fibonacci terms like Fn upon Fn minus 1, this approaches golden ratio. Just like that, as this Fibonacci Pythagorean triple sequence advances, those triples tend to attain the precise proportion of 1 to root 5 triangle. In other words, if phi is the golden ratio in nature, this triangle 1 to root 5 triangle is the golden triangle in geometry. Okay. Before ending this session, I want to mention another interesting aspect of this 1 to root 5 triangle, which is closely associated with golden ratio. All I want to say is that this 1 to root 5 triangle, this special right triangle, is nothing but the geometric expression of golden ratio. As we have seen in the very first part, the angles as well as the side lengths are the precise expression of golden ratio. What I am going to write here is another form of the same thing. Like we have seen the 1 to root 5 triangle, this side is 1, 2 and root 5. Remember the triangle sides 1, 2 and hypotenuse root 5, and see the angles. This is 63.435 degrees and this is 26.565 and so on in degrees. Now see one interesting thing. If we write an equation like this, sine of this angle plus sine function of this angle, sine 26.565 so on degrees plus sine 63.435 degrees bracket. This term plus this term plus square of this term, sine 26.565 plus sine 63.435 and bracket square. Okay, and this whole term, sine 26 degree, sine 63 degree plus the square of this whole term in bracket, and if it is multiplied by 5 and divided by 6, this precisely gives the value of square of golden ratio. Precisely. Okay. We can also write this thing in another form, like sum of two catheti 1 plus 2 upon root 5. Okay. Sum of two catheti upon hypotenuse plus square of this term 1 plus 2 upon root 5 bracket square, and this whole thing multiplied by 5 upon 6. And this is precisely equal to 5 square. Hence, the angles or the Cartesian hypotenuse, everything is the purest expression of golden ratio. Hello, in this part of video, we will see the presence of golden ratio in the in-center, X-center system of this 1, 2, root 5 triangle. As we know, the in-center and 3 X-centers form an orthocentric system. And the in-center, X-center orthocentric system of this 1 to root 5 triangle is full of golden ratio. Okay? And as the in-center and the X-centers are harmonic conjugates, the internal division as well as the external division, which is in form of A plus B upon C. In case of 1 to root 5 triangle, those internal and external divisions are precisely in form of golden ratio. The details of all those golden proportions embedded in various segments of angle bisectors are given in detail in the research paper. So don't forget to visit the paper link. Here I would mention some interesting facts, how the golden ratio is embedded in various length proportions of these 3 angle bisectors. Consider this triangle ABC, typical 1, 2, root 5 triangle. I is the in-center and E1, E2, E3 are 3 X-centers. These points P, Q and R, these are the points where 3 angle bisectors intersect with their corresponding opposite triangle sides. Okay, now let us see how the golden ratio is embedded in various segments of 3 angle bisectors. Like consider this length here from vertex A to X center E1. We'll write down here this length A, E1 upon vertex to in center AI. This ratio is precisely equal to Q of golden ratio. Similarly, consider this from vertex B to X center E2. B, E2 upon the distance between vertex B and in center BI. This is precisely equal to the 4th power of golden ratio. Okay, and similarly this distance C E3 upon vertex C to in center CI. This distance is precisely equal to golden ratio. Every length proportion is the precise expression of golden ratio. Similarly, let us consider the ratios between some other segments of 3 angle bisectors. Like consider this length P E1 upon distance between point P and in center PI. This is also equal to phi Q. Similarly, this distance here Q E2 upon distance of point Q from in center QI. Again, this is 4th power of golden ratio. Similarly, R E3 upon R I. This distance is precisely equal to golden ratio. Golden ratio is precisely ubiquitous in every length proportion of these triangles. So many proportions precisely in terms of golden ratio have been given in the research paper. Don't forget to visit the paper link. For example, I will mention another proportion here. Consider this distance between in center and X center. I E1 upon this distance I P. This distance is precisely equal to 2 phi square. Okay, similarly, distance between in center and this X center I E2 upon this I Q. This is precisely thrice the square of golden ratio. Okay, and similarly, distance between in center and third X center I E3 upon this distance I R. This is phi square. Such precise ratios in terms of golden proportion. In such way, this triangle is full of golden ratio. Every segment of the angle bisector can be expressed precisely in terms of golden proportion. Okay? Now, consider this part. 1, 2, root 5 reference triangle ABC and 3 X centers E1, E2, E3. Here, let us consider the triangle formed by 3 X centers. The triangle E1, E2 and E3. Let us see the beautiful golden geometry of this triangle. The triangle formed by 3 X centers. Okay, let us see the side lengths of this triangle first. Excuse me. Let us see the side lengths. See, side of this triangle E2, E3. This E2, E3 side, it is precisely equal to 4 times cos 18. 4 times cos 18. This side E2, E1. This side is precisely equal to root 2 tan 72. As I have mentioned earlier, these angles 18 degree, 36 degrees, 72 degrees, even 54 degrees and 108 degrees. All these angles are closely associated with golden ratio because these are the angles which are present in regular pentagon, regular pentagram, as well as the golden ratio triangle. Okay, and here the triangle formed by X centers, its sides can be expressed in terms of the trigonometric ratios of these angles. This side E3, E2 is 4 times cos 18. This side root 2 times 72. This side here, this side is precisely equal to root 2 phi plus 1 upon phi. E3, E1. That side is equal to this value. Now let us see the vertices of reference triangle A, B, C. These 3 points divide these triangle sides in an interesting manner. Like this length here, A, E2. This length is precisely equal to tan 72. And this length here, this length A, E3 is precisely equal to tan 36. Tan 36 and tan 72, they add up to this value. Similarly, this length here, C, E2, it is 2 root 2 cos 18. And this length here, C, E1, this length is 2 root 2 sin 36. These two add up to this value. Similarly, this length here, E3 and B, this is root 2 times golden ratio. Okay, and this length here, B, E1, this length here is root 2 upon golden ratio. They add up to this value. One more interesting thing I want to mention here. The points, the vertices of reference triangle A, B, C. The points A, B, C divide these three side lengths in very interesting manner. Like ratios between this CE2 upon CE1. Let me write down. Ratio between these CE2 upon CE1, CE2 upon CE1 is precisely equal to golden ratio. Okay? Ratio between this BE3 upon BE1, BE3 upon BE1. This is precisely equal to phi square. Similarly, AE3 and AE2. The ratio between AE2 upon A. This is 1, this is 3. Here AE2 upon AE3. This is equal to phi cube. Ratio between this and this side, golden ratio. Ratio between this part and this part, square of golden ratio. And ratio between AE3 and AE2 is cube of golden ratio. Such an interesting geometry. And not just sides, even the angles of this eccentric triangle. The triangle formed by three eccentres of this 1 to root 5 triangle. Not just sides, but every angle of this triangle is the precise expression of golden ratio. Like, let us see. This is A, B, C reference triangle, E1, E2 and E3, three eccentres. Let us see the triangles of this eccentric triangle, triangle E1, E2 and E3. Let us see the angles, like this angle here, A, E2, C. This is 45 degrees, or in other words, it is arctangent of 1. Okay. Similarly, this angle here, E2AC, this angle is arctangent of phi precisely, and this angle here, this angle is arctangent of phi cube. Okay. Similarly, this angle here, again, this is arctangent, E3AB, arctangent of golden ratio. This angle here again, this is 45 degrees or arctangent of 1, and this angle AE3B, this is arctangent of phi cube. Similarly, in this is 45 degrees, arctangent of 1. Okay, this angle here is arctangent of phi cube, and this angle here arctangent of golden ratio. Every side length, every angle is the precise expression of golden ratio. Another interesting thing I want to mention about this eccentric triangle. Consider the whole triangle formed by three eccentres. The complete triangle, this E2, E3 and E1. The area of this whole triangle means sum of area of three smaller triangles plus area of reference triangle, which is equal to 1. The area of this whole triangle, area of triangle E1, E2 and E3 is equal to root 5 upon into phi square. Root 5 times phi square. Consider this value. It's an important figure because the area of this eccentric triangle is root 5 times phi square. You consider this figure root 5 phi square, because in case of 1 to root 5 triangle, the area of its Gergon triangle is equal to the area of its Nagel triangle is equal to 1 upon root 5 times phi square. You must know about Gergon triangle. Gergon triangle is formed by 3 in-touch points. The 3 points where the in circle of the triangle touches the sides. Area of Gergon triangle of 1 to root 5 triangle is this value. Inverse of this. This is the area of larger X-centered triangle. And inverse of it is the area of Gergon triangle. It is also equal to area of Nagel triangle. Nagel triangle means where 3x circle touch the triangle side like this. 3 x touch points. 3 points where 3x circle touch the reference triangle sides, that is Nagel triangle. Area of Nagel triangle is equal to area of Gergon triangle, which is inverse of this value, which is area of the X-centered triangle. Okay, and more interesting thing about this figure. This is the X-centered triangle of 1 to root 5 reference triangle, and this is the Gergon triangle of this 1 to root 5 reference triangle. There is a definite ratio between the corresponding sides of X-centered triangle and Gergon triangle, and that ratio is root 5 phi square. Like ratio between Gergon triangle side and X-centered triangle side is precisely this figure. Corresponding side of X-centered triangle upon that corresponding side of Gergon triangle is precisely this value. Such an interesting geometry of this 1 to root 5 reference triangle. Another thing I just want to mention here, if we extend the sides of this Gergon triangle, we extend the sides of Gergon triangle and we extend the sides of reference triangle, we get 3 points where reference triangle sides and Gergon triangle sides meet each other, and we call those points as knobs points. We call those points as knobs points. The knobs points are denoted by N1, N2 and N3, and these 3 knobs points are always collinear. The line is known as Gergon line. I am not going to elaborate here, the details are given in paper, but I would like to mention these 3 knobs points, and the Gergon line of this 1 to root 5 triangle is also full of golden ratio. Every angle, every side length, every distance concerning with Gergon line and 3 knobs point are the expression of golden ratio. Such a beautiful geometry of this 1 to root 5 triangle. And hence I got a question for every viewer of this video, for each of you, for all of you. I got a question for you. So far we have seen the golden geometry of this 1 to root 5 triangle. Every angle, every geometric aspect, every single side length, every distance is simply the expression of golden ratio. And hence I just want to ask you guys one simple question. This term, golden ratio triangle, this title is generally given for an isosceles triangle like 36 degree, 72 degree and 72 degree. This isosceles triangle is generally known as golden ratio triangle because these 2 sides, each of these side is in golden proportion with this unequal side. Okay. On one hand, this triangle is known as golden ratio triangle, and on other hand we have our very special, or say sui generis 1 to root 5 triangle, whose every geometric aspect is full of golden ratio. So my question is, in your opinion, this appellation or this title is suitable for which of these 2 triangles? This epithet is more suitable for this generally accepted triangle, or this appellation or this title is more suitable for this sui generis 1 to root 5 triangle. The answer of this question, I leave it to your wisdom and your fine sense of judgment. Keep watching and don't forget to visit the paper link which is provided in video description. Thank you. Hello. So far we have seen the golden geometry of this 1 to root 5 triangle and how the golden ratio is geometrically substantiated in form of this special right triangle. In this part we are going to see that not just golden ratio but every other metallic mean or every metallic ratio can be geometrically substantiated in form of a special right triangle. Okay? As you may know, just like golden ratio, there are several other metallic ratios like this delta 1, which is equal to golden ratio, and its value is 1.618039 and so on. Just like golden ratio, there are successive metallic means like delta 2, the second metallic mean, which is also known as silver ratio, and its value is 2.4142 and so on. The third metallic ratio, which is also known as bronze ratio, and whose value is 3.302775 and so on. And further, the copper ratio and other metallic means. Infinite series of such metallic ratios. Okay? Now, these metallic ratios, their precise values are given by a well-known formula. The formula is like this. Any nth metallic mean, value of any metallic mean is equal to n plus square root of 4 plus n square upon 2. A well-known formula to determine the precise value of any metallic ratio, or these metallic ratios are also expressed in form of continued fraction. Continued fraction for golden ratio is like 1 plus 1 upon 1 plus 1 upon 1 plus 1 upon and so on. And in similar way, there are continued fraction expressions for other ratios also. In this part, what I want to elaborate is every metallic mean, each of these metallic ratio can be expressed by a special right triangle, just as golden ratio is precisely expressed in form of 1 to root 5 triangle. Consider here a right triangle like a right triangle having one of its catheti is 1. This is hypotenuse, and the other cathetus of this right triangle is 2 upon n. Look at two catheti of this triangle, 1 and 2 upon n. And such right triangle can precisely express any nth metallic ratio by this formula delta n. Value of that nth metallic mean is equal to this cathetus 1 plus hypotenuse upon the second cathetus 2 upon n, and that value we get from this formula the value of nth metallic mean which we get from this special right triangle is precisely equal to this value. Okay, let me elaborate. Like we can represent the second metallic mean by a right triangle whose catheti are 1, 1 and hypotenuse is root 2. This triangle can represent silver ratio, like silver ratio is equal to this cathetus 1 plus hypotenuse upon the second cathetus 1 or 2 upon m. Okay, and this value is precisely equal to 2.4142 and so on. Similarly, the right triangle with its catheti 1 and 2/3 can precisely represent the bronze ratio. Okay, and not just determination of the values of metallic means, we can also generalize other features of this right triangle which represents all metallic means. Just like consider the right triangle for silver ratio 1, 1, root 2, an isosceles triangle. Okay, we had seen the in radius of this golden ratio triangle which was equal to 1 upon phi square, or this can be also written as 1 upon 1 plus golden ratio. Just like that, the in radius of this silver ratio triangle can also be written as in radius r is equal to 1 upon silver ratio plus 1. The things can be generalized like this. Okay, even if you remember, we had derived a wonderful equation. The area of this golden ratio triangle, area of this golden ratio triangle or 1 to root 5 triangle upon the area of its incircle. We had determined this ratio precisely equal to phi raised to 4 upon pi. These things can also be generalized for every metallic ratio. Like here in this silver ratio triangle, we can generalize the things like area of silver ratio triangle upon area of its incircle is also precisely equal to the square of silver ratio upon pi. Okay, everything can be generalized. More importantly, you guys must remember, we had considered the Fibonacci Pythagorean triples while elaborating the golden geometry of this 1 to root 5 triangle. I had mentioned about the Fibonacci Pythagorean triples. The Pythagorean triples with alternate Fibonacci numbers as their hypotenuse, and such series of Pythagorean triples derived from Fibonacci numbers approach to attain the specific proportions of 1 to root 5 triangle. See the analogy. Just like that, if we derive Pythagorean triples using pale numbers, this pale number sequence is closely associated with silver ratio. Okay, and if we derive Pythagorean triples with alternate pale numbers as their hypotenuse, the triples like 3, 4 and 5, Pythagorean triple with pale number as hypotenuse, another triple like 20, 21 and 29, one more triple like 119, 120, 169 and so on. Infinite Pythagorean triples can be derived with alternate pale numbers as their hypotenuse. And the more important thing is that as such series of these Pythagorean triple advances, the triples so formed approach to attain the specific proportion of silver ratio triangle, which is 1, 1 and root 2. as a series of Pythagorean triples with alternate pale numbers as their hypotenuse. As such series advances, the triples so formed attain the proportion of silver ratio triangles. Means these two catheti approach to attain the proportion 1:1. In other words, just like the pale sequence advances, and the consecutive pale numbers like Pn upon Pn minus 1 approaches the silver ratio. In the same way, as the series advances, the triples so formed approach the proportions of silver ratio triangle. In other words, if this number 2.4142 is the silver ratio in nature, this triangle, the silver ratio 1/√2 triangle, is the specific silver ratio triangle in geometry. Okay? Now, let us see how the generalized metallic ratio triangle can express the value of that particular metallic mean in specific ways. Every geometric aspect of this metallic ratio triangle can be generalized, just like the golden ratio triangle, as I have shown here. This 1 to √5, it's a golden ratio triangle, and it typically represents the golden ratio. Just like that, here is the generalized metallic ratio triangle. The generalized metallic ratio triangle, and every geometric aspect of this triangle can be generalized. Let us see the comparison between these two things. As we have seen in very first part of this video, the side lengths of this golden ratio triangle provide the fractional expression of golden ratio, and every side and every angle of this triangle is the purest expression of golden ratio. Like I had mentioned, the in-touch points of circle. The in-touch points of in circle divide the side lengths of golden ratio in very specific manner. Like this length here from touch point to vertex C was golden ratio, just like this length, touch point to vertex C. This length here, B to this touch point and B to this touch point, it was equal to in radius 1/pi square. And these lengths here, tangents to the in circle from point A, this and this, these lengths were precisely 1/pi square. All these things can be generalized in the generalized metallic ratio triangle. Like suppose A, B, C is the generalized metallic ratio triangle. I is the in center, and this P, Q, R are the touch points of in circle. Then these distances can also be expressed just like golden ratio triangle, like this QC and this RC. Means tangent from vertex C to the in circle, they can be expressed in terms of this value, 1 / that particular metallic ratio minus 1, QC and RC. Similarly, these distances BP and PR, they are equal to in radius of this generalized triangle, and its value is, as I mentioned earlier, it is 1 / that metallic mean plus 1. Similarly, these portions of triangle sides AQ and AP, they are analogous to this 1/phi square, and these portions can be expressed in terms of this value, 1 / that metallic ratio minus n minus 1. And not just side lengths, even the angles can be generalized. Like consider this acute angle here, the acute angle of the generalized metallic ratio triangle, the angle against cathetus 1. This angle can be precisely expressed as twice the arctangent of that metallic ratio minus 90 degrees. twice the arc tangent of that metallic ratio minus 90 degrees. This value is 26.565 degrees for golden ratio triangle, or this value is 45 degrees for silver ratio triangle. Similarly, this angle, the angle opposite to the catheti 2 upon n. This angle can be given by generalized formula twice the arc tangent of inverse of that metallic mean. Twice the arc tangent of inverse of that metallic mean. And this value is 63.435 degrees for golden ratio triangle, 45 degrees for silver ratio triangle, and so on. And not just angles or sides or the side length division by Gergon triangle vertices, every other thing of this generalized metallic ratio triangle can be generalized. Okay, let us see. For example, area of this generalized metallic ratio triangle. Area of this triangle is simply equal to 1 upon. Okay, and as I mentioned here, the in radius of this generalized metallic ratio triangle is precisely equal to that metallic mean plus 1 inverse of it. The in radius is 1 upon that metallic ratio plus 1. Semi-perimeter of this generalized metallic ratio triangle is equal to that metallic ratio upon metallic ratio minus 1. All figures which I have seen in case of golden ratio triangle, they can be generalized like this. For example, this value was 1. Area of golden ratio triangle was 1. It can be generalized as 1 upon n. This value for golden ratio triangle, the in radius of golden ratio triangle was 1 upon 5 square. It can be generalized for the generalized triangle as 1 upon metallic mean plus 1. This value for golden ratio triangle was 5 square. It can be generalized here as that metallic ratio upon that metallic ratio minus 1. And more interestingly, the ratio between the areas of metallic ratio triangle upon the area of its incircle, the area of that particular metallic ratio triangle, okay, upon the area of its incircle. It can be also represented as generalized formula like area of triangle upon area of its incircle. It is precisely equal to that metallic ratio plus 1 bracket square upon n times value of pi. Okay, this value comes to be 5 raised to 4 upon pi for golden ratio triangle, or this value comes to be square of silver ratio upon pi for silver ratio triangle, and so on. Hence, all these things can be generalized. What we have seen in the classical geometry of 1 to root 5 triangle, everything can be generalized for any metallic mean, as the spatial right triangle whose catheti are 1 and 2 upon n precisely represents the nth metallic mean. The details of all this stuff are provided in the research paper, so don't forget to click the paper link in video description and keep watching this video. Thank you. Hello. So far we have seen the golden geometry of 1 to root 5 right triangle. Okay, in this part we are going to see the classical geometric relationship between a couple of right triangles, the classical geometric intimacy between 1 to root 5 triangle and 3, 4, 5 Pythagorean triple, which is the first of primitive Pythagorean triples. Now I would like to mention these two right triangles are observed to be invariably forming together by various geometric methods. These two triangles are formed together by different geometric methods, and several such methods I have described in my paper. In this session, I am going to describe a couple of such methods in short. Like, consider the reference triangle ABC, which is 1, 2, root 5 right triangle. Okay, and since it's a right triangle, this point B, it is also the orthocenter of this triangle, and the midpoint of hypotenuse, point O, it is the circumcenter of this triangle. Okay, hence line BO is the Euler line of this triangle, and importantly, this BO is also the median on hypotenuse. I repeat, 1, 2, root 5 right triangle, hence B, vertex B is the orthocenter, midpoint of hypotenuse O is the circumcenter, line BO is the Euler line, and the smallest median or the median on hypotenuse, that BO, that coincides with this Euler line. Now, this BP is the angle bisector of this right angle. Okay, and this line BQ, this is altitude on hypotenuse. BP is angle bisector of right triangle and BQ is altitude on hypotenuse. Interestingly, this BQ is also the symmedian, because these two angles PBQ and PBO are equal. Hence BQ is altitude on hypotenuse and this BQ is also the symmedian. Now, interestingly, this triangle formed here, BOQ, is 3, 4, 5 Pythagorean triple. Angle BOQ is a 3, 4, 5 Pythagorean triple. In other words, in 1, 2, root 5 right triangle, the median on hypotenuse and the symmedian produce a 3, 4, 5 Pythagorean triple, or the Euler line and the altitude on hypotenuse produce 3, 4, 5 triple. In this way, the 3, 4, 5 Pythagorean triple is formed inside the 1, 2, root 5 right triangle. There are several other methods, like if we draw a perpendicular on Euler line like this, perpendicular on Euler line from vertex A. Suppose AS is the perpendicular on Euler line from vertex A. In this case, this triangle ASO formed here is a Pythagorean triple. Okay, because this angle is precisely 53.13 and so on degrees, which is the angle of Pythagorean triple. So this triangle formed here, ASO, is 3, 4, 5 Pythagorean triple, and it is also accompanied by the formation of a 1, 2, root 5 triangle. This triangle here, ASB, it is 1, 2, root 5 triangle. Similarly, if we draw perpendicular from vertex C on Euler line, like CR, is perpendicular from vertex C on Euler line, and if we connect vertex C to D Longchamps point, D Longchamps point means point X20 in Kimberling Encyclopedia. Okay, perpendicular from vertex C on Euler line, and if we connect vertex C to D Longchamps point, in this case, this triangle COR is 3, 4, 5 triangle, and CDR is 1, 2, root 5 triangle. In this way, these couple of triangles are formed together by different geometric methods, which I have described in detail in my paper. So visit the paper link. Here I am going to elaborate the most important method of concurrent geometric formations of these two triangles, and that most important method is a simple dissection of a square. Okay, consider here, consider square A, B, C and D. For ease of explanation, for ease of illustration, the side of this square is taken as twice the square root of 5. Side of square here is twice the square root of 5, but what I am going to say is true for any square. Consider square A, B, C and D. P is the midpoint of side AD and R is the midpoint of side DC. Alright, so far so good. Now let's connect point P to vertices B and C, PB and PC. We connected this midpoint to vertices B and C, and we connect vertex B to point R, which is midpoint of DC. Okay, such simple dissection of square by 3 lines, PB, PC and BR. This simple dissection of a square by 3 line segment gives us interesting geometric figure, like this triangle formed here in center, triangle PBQ. This is precisely a 3, 4, 5 Pythagorean triple. Okay, and all other triangles formed in this figure are precisely the 1, 2, root 5 triangles, like this triangle CQR, CPD, CRB, CQB, ABP. All other triangles formed here are 1, 2, root 5 triangles of different sizes. Another interesting thing, consider these 3 triangles, 1, 2, root 5 triangles like CRQ, CQB and ABP. These 3 angles are in specific proportion with each other. Their side lines are in specific proportion with each other. These 3 triangles. And because of their side lines, also their perimeters, semi-perimeters, their in radii, their x radii, all are in specific proportion with each other. And the proportion is 1, 2 and root 5. Such a simple dissection of square, giving such a classical geometry. So these 1, 2, root 5 triangle are in specific proportion 1, 2, root 5 with each other. The central triangle produced here is Pythagorean triple. Another interesting thing, you can notice beside this 1, 2, root 5 triple and multiple 1, 2, root 5 triangles, 2 irregular quadrilaterals are formed in this figure. Irregular quadrilateral A, B, Q, A, P, Q and B. This quadrilateral here. Alright. And another quadrilateral P, D, R, Q. This quadrilateral here. This part and this part. Prima facie, these 2 quadrilaterals seems to be irregular quadrilateral, but they possess some interesting geometric features, like these are right triangle here, this one and this one. Other 2 angles of these irregular quadrilaterals are this angle here and this angle here, angle APQ and angle DRQ. Both are precisely equal to 116.565 degrees, which is equal to twice the arctan of golden ratio. Okay, and these 2 triangles here, triangle ABQ and angle ABQ and angle DPQ. These angles are precisely 63.435 so on degrees, which is twice the arctangent of the inverse of golden ratio. Okay, so many interesting things are there. Now, even we find the precise golden ratio embedded inside dissected square, like this. Let me elaborate. Consider these sides. Consider this irregular quadrilateral A, B, Q, P. and another quadrilateral PQRD. We can notice here the golden ratio is not just embedded in angles of this quadrilateral, but the golden ratio is observed also in the side length of these quadrilaterals, like these sides AB and BQ. AB plus BQ upon this side AP upon PQ, AP plus PQ, sum of two longer side and sum of two smaller side. Similarly, this is equal to sum of two longer sides like PD and PQ, PD plus PQ upon DR plus RQ, DR plus RQ, and these two values are precisely equal to golden ratio. Alright, it's not just angles of this quadrilateral, but the side length proportions of these two quadrilaterals are the expression of precise golden ratio. In other words, consider this quadrilateral A, P, Q, B. What we have seen, the golden proportion between the angles as well as corresponding sides of this quadrilateral. We can say it in other words also. Like if we connect 1, 2, root 5 triangle and equivalent size 3, 4, 5 triangle along their common hypotenuse. I repeat, if we connect 1, 2, root 5 triangle and 3, 4, 5 triangle of equivalent size along their common hypotenuse, the corresponding sides and the corresponding angles are the precise expression of golden ratio. Let me elaborate. Consider here, in this diagram, this triangle ADC is a 3, 4, 5 Pythagorean triple. Okay, this is right triangle. And this triangle ABC is a 1, 2, root 5 triangle of equivalent size. This is common hypotenuse. Okay, and in this case, we can say AB, this side of 1, 2, root 5 triangle, and this side of Pythagorean triple AB plus AD upon the smaller cathete of two triangle BC plus CD precisely equals to golden ratio. And not just side lengths, also the corresponding angles. Two corresponding angles, two smaller acute angles of these two triangles, 26.565 degrees and 36.87 degrees. They add up to precisely twice the arc tangent of inverse of golden ratio. And larger acute angles, this is 63.435 degrees and this is 53.13 degrees. These two larger acute angles of these two triangles precisely add up to twice the arc tangent of golden ratio. Such is the classical geometric relationship between these two triangles, the 1, 2, root 5 triangle and 3, 4, 5 primitive Pythagorean triple. The details of this classical intimacy between these two triangles is given in the paper. So visit the paper link. Here I want to mention one more thing that corroborates the classical geometric relation between these two triangles. Like consider this quadrilateral APQB. This quadrilateral is composed of these two triangles. This triangle here, triangle APB, is the 1, 2, root 5 triangle. Triangle APB is 1, 2, root 5 triangle. And this triangle here, PBQ. This is 3, 4, 5 Pythagorean triple. Look at the angles of these triangles. In this 1, 2, root 5 triangle, this angle, the larger acute angle, it measures 63.435 and so on degrees, and the smaller acute angle 26.565 degrees. Similarly, in 3, 4, 5 Pythagorean triple, the larger acute angle 53.13 degrees, and this angle here is 36.87 degrees. Okay. Now consider the quadrilateral APQB, which is made up of these two triangles, 1, 2, root 5 triangle and 3, 4, 5 triangle. In this quadrilateral, PB is the diagonal. If we introduce second diagonal AQ in this quadrilateral APQB, PB is the first diagonal, which is common hypotenuse of these two triangles. Now if we introduce second diagonal AQ like this, second diagonal AQ, here it is observed that this second diagonal AQ divides the right angle in each triangle into the smaller angles of its complementary triangle. I repeat, the second diagonal AQ divides the right angle in each triangle into the smaller angles of its complementary triangle. Like this angle is 53 degree here, 53.13 degrees. This angle is also 53.13 degrees. This angle, look at this angle, the smaller acute angle of Pythagorean triple. This angle is also 36.87 degrees here, precisely. Similarly, this larger acute angle of 1, 2, root 5 triangle, this angle here is also 63.435 degrees. This angle, smaller acute angle of 1, 2, root 5 triangle, this angle is also 26.565 degrees. In other words, the second diagonal AQ divides the right angle of 1, 2, root 5 triangle into two acute angles of 3, 4, 5 Pythagorean triple, and vice versa. Such is the classical geometric intimacy between these two triangles. Details of this classical geometric relationship are given in the paper, so don't forget to visit the paper link and keep watching this video. Let us see you in the next part of this video. Thank you. Hello. In last part of this video, we saw the classical geometric relationship between these two triangles, 1, 2, root 5 triangle and 3, 4, 5 Pythagorean triple. In this part, we are going to see some detailed geometric features of these two triangles, which enable them to combinedly impart the precise value of golden ratio. Alright. First, let us see the side lengths of these two triangles. As we have seen in very first part of this video, the side lengths of 1, 2, root 5 triangle are the precise expression of golden ratio. Like this cathetus 1, this is precisely equal to inverse of golden ratio 1 upon phi plus 1 upon phi square. Okay. Similarly, this cathetus 2, this is also precisely equal to golden ratio plus 1 upon square of golden ratio. And the hypotenuse root 5, it is precisely equal to golden ratio plus inverse of golden ratio. And this hypotenuse root 5, it can also be written as square of golden ratio minus inverse the square of golden ratio. Alright. And just like 1, 2, root 5 triangle, the sides of 3, 4, 5 Pythagorean triple, they can be also expressed in precise terms of golden ratio. Like this side 3, it is precisely equal to 5 square plus 1 upon 5 square. Okay. This side, the longer cathode 4, this is also precisely equal to 5 cube minus inverse of 5 cube. Okay. And the hypotenuse 5, this is also precisely equal to root 5 times golden ratio plus root 5 upon golden ratio. Got it? All 6 side lengths of these classically related triangles can be precisely expressed in terms of golden ratio. And not just 3 sides, even the angles of these 2 triangles are the precise expression of golden ratio. We have already seen how the angles of 1, 2, root 5 triangle can be expressed in terms of golden ratio. All 4 acute angles of these 2 right triangles can be expressed in terms of golden ratio. Like here, the larger acute angle of 1, 2, root 5 triangle. This is 63.435 and so on in degrees. This angle is precisely equal to twice the arctan of the inverse of golden ratio. And we have also seen this angle is 26.565 and so on in degrees. This angle is also precisely equal to twice the arctangent of the inverse of the cube of golden ratio. Okay. More important thing is here, not just these 2 triangles, but the acute angle of 3, 4, 5 Pythagorean triple. This can also be expressed in terms of golden ratio. All acute angles can be expressed in terms of arctangent of phi raised to n or 1 upon phi raised to n. And n is equal to odd powers of golden ratio, like n is equal to 1 or n is equal to 3 or n is equal to 5 and so on. Let me elaborate. This angle, the larger acute angle of 1 to root 5 triple, this can be written as twice the arctangent of inverse of golden ratio. It can be also written as the arctangent of phi cube minus the arctangent of 1 upon phi cube. Okay. Now let us see the acute angles of 3, 4, 5 Pythagorean triple. This angle here, this is 53.13 degrees, and this angle can also be expressed in form of the odd powers of golden ratio. Like this 53.13 degrees, this angle is precisely equal to arctangent of the 5th power of golden ratio minus arctangent of the inverse of golden ratio. Also, this is exactly equal to the arctangent of golden ratio minus arctangent of 1 upon 5th power of golden ratio. Okay. Now another acute angle of 3, 4, 5 Pythagorean triple. This 36.87 and so on in degrees. This angle is precisely equal to arctangent of 1 upon 5th power of golden ratio plus arctangent of 1 upon golden ratio. This angle can be also written as twice the arctangent of phi cube minus the arctangent of phi. Just like all sides, all four acute angles can be precisely expressed in terms of golden ratio. More specifically, odd powers of golden ratio 1, 3 and 5. Alright, I just want to mention another remarkable thing here. Consider these four acute angles. This angle, smaller acute angle of Pythagorean triple, is the complementary angle for twice of this angle. Twice of this 26.565 degrees plus 36.87 degrees. They add up to 90 degrees. I repeat, this angle of Pythagorean triple is complementary angle for twice of this angle. Similarly, this angle of Pythagorean triple is the supplementary angle for twice of this angle. Twice of this angle and this angle of Pythagorean triple, they add up to 180 degrees. Another important thing, look at these two smaller acute angles. Two smaller acute angles of these two triangles, they add up to the larger acute angle of 1 to root 5 triangle. 26.565 degrees and 36.87 degrees, they add up to this acute angle. Okay? And another last important thing, twice of this angle, twice of smaller acute angle of 1 to root 5 triangle is equal to larger acute angle of Pythagorean triple. Such a classical intimacy. And hence, when we dissect these two triangles, we always get a couple of 1 to root 5 triangle plus one Pythagorean triple. Dissection of these two triangles impart couple of these angles and one Pythagorean triple. All right? Okay. Hello. Here, I just want to mention a couple of things regarding the classical geometric relationship between these two triangles. 1 to root 5 triangle and 3, 4, 5 Pythagorean triple. Look at the catheti of these two triangles. 2, 1, 3 and 4. These are exactly first four Lucas numbers. The first four terms of Lucas sequence. And as we know, the Lucas numbers are more closely associated to golden ratio, more closely than Fibonacci numbers. Like as the Lucas series advances, the nth Lucas numbers tends to be nth power of golden ratio. Lucas numbers are more closely associated with golden ratio than Fibonacci numbers. And catheti of our two classical triangles are first four Lucas numbers. But I must mention here, if we construct such couple of triangles using four consecutive Lucas numbers, if we construct such couple of triangles using any other four consecutive Lucas numbers like ln plus 1, ln plus 2 and ln plus 3. Couple of triangles whose catheti are 4 consecutive Lucas numbers or 4 consecutive Fibonacci numbers or 4 consecutive terms of any other generalized series where ratio between 2 consecutive terms xn upon xn minus 1 is equal to golden ratio. 4 terms of any such series are the catheti of 2 couple of triangles. I must mention here, none of these triangles, none of such triangles exhibit the classical geometric relationship we have seen so far between these 2 special triangles. If we construct couple of triangles with 4 consecutive Lucas numbers as their catheti or 4 consecutive Fibonacci numbers as their catheti, none of those triangle couple exhibit that classical relationship which we have seen between these 2 triangles, because the precise ratio between the consecutive terms of Lucas series or the consecutive terms of Fibonacci series is never precisely equal to golden ratio. It approaches golden ratio as the series advances, but it is never precisely equals 5. And the classical geometric relationship we have seen between these 2 triangles is precise, extremely precise and entirely accurate up to infinite decimal places. And that corroborates, that authenticates and that underlines the importance and uniqueness of the classical geometric intimacy between these 2 triangles. Okay, one more thing I want to mention. You must have heard about doubling of the triangle, doubling of the angle. If an acute angle of a right triangle is doubled, its hypotenuse gets squared. Like, consider a triangle, right triangle. This is right angle, this is hypotenuse h, and this is the acute angle theta. Now, if we double this angle, the hypotenuse of the new right triangle produced is h square. Let me explain. Consider our 1, 2 and root 5 triangle. Okay, this angle here in 1, 2, root 5 triangle is 26.565 and so on degrees. Now, if we double this angle theta from 26 degrees to 53.13 degrees, if we double this angle theta, the hypotenuse gets squared, root 5 to 5. If this catheti here is equal to x and this catheti of original triangle is equal to y, the hypotenuse becomes x square plus y square. This is equal to 5. The catheta is 4. This is equal to twice xy, and the another cathetus of new triangle form 3. This is equal to x square minus y square. Okay, doubling this angle theta, the hypotenuse gets squared, and this is the geometric relationship between these 2 triangles. Now, however, so many other triangle couples are formed on same principle, like 1, 2, root 5 and 3, 4, 5 triangle couple is the classical example of such couple. There are so many other couples which are formed on same principle, like 2, 3, root 13 triangle and 5, 12, 13 Pythagorean triangle. This couple of right triangles are also formed on same principle like our classical triangles. Another example, 1, 3 and root 10 triangle and 6, 8 and 10 Pythagorean triple. This couple of triangle is also formed on same principle. One more example. 1, 4, square root of 17 triangle, and 8, 15 and 17 Pythagorean triple. Look at these triangle couples. This and this Pythagorean triple. This and this Pythagorean triple. There are infinite triangle couples which can be formed on basis of same geometric principles. If the acute angle is double, the hypotenuse gets squared. But again, I want to mention here, the classical geometric relationship which is observed between these two triangles is not exhibited by any other such couple. None of other such couple exhibit the classical geometric relationship which is given by these two triangles. The classical intimacy we have seen so far is the exclusive property of these two triangles, and of course their multiples also. Hello. In this part, I am going to describe a calculator trick, a well-known calculator trick which can be correlated with the classical correspondence between these two triangles. The 1, 2, root 5 golden triangle and the ubiquitous 3, 4, 5 Pythagorean triple. Okay. In previous part of this video, we had seen if these two triangles of equivalent sides are connected along their hypotenuse like this, the 1, 2, root 5 triangle and 3, 4, 5 Pythagorean triple with their common hypotenuse, these triangles exhibit the golden ratio precisely embedded in their side lengths as well as their angles, like the sum of longer catheti upon sum of shorter catheti is precisely equal to golden ratio, and also their corresponding angles add up to exhibit a precise value of golden ratio. In this part of video, what is important for us here is that the ratio between the areas of equivalent sized 1, 2, root 5 and 3, 4, 5 triangles. The ratio between the areas of these two equivalent sized triangles is invariably 5:6. If they have common hypotenuse, the ratio between their areas is invariably 5:6. Just keep this thing in mind. Now, you guys must have heard about a fluky equation like 6/5 phi square approximately equals the value of pi. Okay, this is an imprecise equation, or you can call this a coincidental equation. But you search on Google like pi phi correlation, you will get the equations like this: 6/5 phi square approximately equals the value of pi. This is fluky, this is incorrect equation. Okay, then why we are discussing here? Because everything we have discussed so far is entirely accurate and precise up to infinite decimal places. Then why we are discussing this inaccurate equation here? Let me elaborate. There is a famous calculator trick like if you type 5, 5, 5, 5, 5, such n times 5, make inverse of it and get either sine or tangent of it. You will get a pi-like value on your calculator screen. A value that looks like pi. I repeat, if we get sine or tangent of 1 upon 5, 5, 5, 5, 5, 5, n times 5. We will get the value which looks like pi, or more precisely pi into 10 raised to minus n plus 2. Alright, it's a well-known calculator trick. What is important here? If we replace this digit 5 by 6, if we get sine or tangent of 1 upon 6, 6, 6, 6, 6, 6, 6, n times 6. Okay, here we get the value which looks like phi square into 10 raised to minus n plus 2. And of course, this formula we have seen here, when we replace 5 by 6, we get figures which look like phi square, and this equation can be generalized for any digit, not just for 6. If we get sine or tangent of any digit k, n times k, we get the formula like 6 upon k phi square into again 10 raised to minus n plus 2. What we're getting with digit 6, we can get the same thing with any digit k just by placing here 6 upon k. Okay, and of course this is not the precise value of phi. Such equations do not give us precise value of phi. What is remarkable here is if we put this value of phi or this value of square of golden ratio into this fluky equation, we get the value of pi which is precise up to n minus 1 decimal places. Let me write down sine or tangent of 1 upon 6, 6, 6, 6, n times 6. Okay, and this thing multiplied by 6 upon 5 is equal to pi into 10 raised to minus n plus 2. And remarkably, this value of pi we get here is precise up to n minus 1 decimal places. If we type 1000 times 6666666, we will get 999 decimal places accurate value of pi. Okay, this is of course incorrect equation, fluky equation or imprecise equation. What is remarkable here that this figure, this 6 upon 5, is precisely the ratio between the areas of equivalent size 1 to root 5 golden triangle and 3, 4, 5 ubiquitous Pythagorean triple. That is the significance of this 6 upon 5. And not just up to here, these two triangles, the golden triangle 1 to root 5 and the Pythagorean triple 3, 4, 5, the classical correspondence between these two triangles also enables us to derive the precise pi correlation. How? That we'll see in the last part of this video. But I repeat what I just said. Although pi is a transcendental number and golden ratio is an algebraic number, the classical geometric relationship between these two triangles enables us to get the precise pi-phi correlation, which is firmly based upon classical geometric principles, and that will be the paramount validation of the classical intimacy between these two triangles. We will see that in last part of this video. So please keep watching and don't forget to visit the paper link. Thank you. Hello. On this part of the video, we will see how this triangle 1, 2, root 5 can be exploited to derive the precise pi-phi correlation. And the correlations we are going to talk here are not like some fluky or imperfect equations like 6 upon 5 into square of golden ratio approximately equals the value of pi, or another famous but imprecise equation like 4 upon pi, which approximately equals the square root of golden ratio. We are not going to talk about such equations. We are going to talk about the precise pi-phi correlation which can be derived using this special right triangle 1, 2, root 5. As we know, this right triangle with its cathete in proportion 1:2 is full of golden proportions. Like semi-perimeter of this triangle is equal to square of golden proportion, or the in radius of this triangle is equal to inverse of the square of golden proportion. Okay. In such case, if we incorporate the incircle in this triangle, with incircle naturally pi enters into picture, and thence we can derive the precise pi-phi correlation like this. Consider this reference triangle ABC, which is 1, 2 and root 5 triangle, and this is the incircle of this triangle. Here it is observed that the area of this triangle ABC upon the area of its incircle, it is equal to perimeter of this triangle upon circumference of the incircle, and it is precisely equal to the 4th power of golden ratio upon pi. See this beautiful equation. It is precise up to infinite decimal places. And if we consider a couple of such triangles, like here, triangle ABC and triangle ADC with their common longer cathetus AC. This is hypotenuse root 5 of this triangle. This is hypotenuse root 5 of triangle ADC. This side 1, 1, and this is common longer cathetus 2. And if we incorporate the incircle in this combined triangle ABD, here also we observe a precise correlation, like area of this triangle ABD upon area of its incircle. This is precisely equal to twice the square of golden ratio upon pi. Okay. And in case of common shorter cathetus, consider these two triangles ABC and ADC. This is hypotenuse, of course, root 5 and root 5. This is the longer cathetus, BC equal to 2, DC equal to 2. This is shorter cathetus, AC. And we incorporate the incircle in this combined triangle. In this case, the ratio between the area of triangle ABD upon the area of its incircle, it is precisely equal to the 6th power of golden ratio upon twice the value of pi. Extremely precise correlations. And same are the relations between perimeter of these triangles and circumference of their incircles. Okay. And not just incircles, even the x circles. If we consider x circle of this 1 to root 5 triangle, those x circles can also provide this precise pi-phi correlation, because the 3x radii of this triangle are nothing but different powers of golden ratio. Like 3x radii of this 1 to root 5 triangle are square of golden ratio. The second x radii is precisely equal to golden ratio, and the third x radius is inverse of golden ratio. Hence, the classical geometry of this 1 to root 5 triangle enables us to derive the precise pi-phi correlation, which is firmly based upon classical geometric ratios. Details of all these things are provided in the research paper, and the paper link is in video description. So kindly visit the paper link and keep watching this video. Thank you. Hello. In last part of this video, we have seen how this 1 to root 5 triangle can be used to get the precise correlation between golden ratio and pi. The precise geometric ratios between this 1 to root 5 triangle and its incircle is observed in form of this equation. Similarly, if we connect couple of these triangles, if we connect couple of 1 to root 5 triangles along their longer catheti, here also we find a precise ratio between the combined triangle and its incircle in form of this equation. And if we connect two such triangles along their shorter catheti, the ratio between the combined triangle and its incircle is in this form. So this 1 to root 5 triangle can be exploited to get the precise pi-phi correlation in terms of geometric ratio. And this is obvious because in radius of this triangle is precisely equal to 1 upon phi square. So these ratios are obvious. But more important thing is that the similar precise pi-phi correlations, the similar correlations between pi and the golden ratio can also be derived from these couple of triangles, the 1 to root 5 triangle and 3, 4, 5 triangle. Like this, consider this triangle A, B and C. This is 1 to root 5 triangle. In this triangle ABC, this is 3, 4, 5 Pythagorean triple. If we connect this triangle with their common longer catheters AC, 1 to root 5 triangle and 3, 4, 5 triple with their common longer catheters AC, and if we incorporate the incircle in this combined triangle ABD, here also we observe the similar precise correlation, like area of this triangle ABD upon area of its incircle this is precisely equal to twice pi square upon pi. Okay, and here we connect the two triangles along their smaller catheters. This triangle PQR, this is 1 to root 5 triangle, and the triangle PRS is the 3, 4, 5 Pythagorean triple, and these triangles are connected along their smaller catheters PR, and we incorporate the incircle. Here in this case, the precise ratio observed between the area of triangle, the combined triangle PQS, and the area of its incircle is like this: 3 phi square upon pi. The similar precise pi-phi correlations with common smaller catheters and common longer catheters, and these are the paramount validation of the classical geometric relationship between these two triangles. Okay, I would like to mention, no other geometric figure can give us such precise pi-phi correlation. For example, see the square here, a typical square and incircle inscribed in that square. In this case, the ratio between the area of this square and area of its incircle is 4 upon pi. And the coincidental equation or the fluky relationship is well known. This 4 upon pi is approximately equals the square root of golden ratio, but not precisely. This is not precise equation. So square or any other geometric figure cannot provide precise pi-phi correlation. Only and only this classical 1, 2, root 5 triangle alone, or in amalgamation with 3, 4, 5 Pythagorean triple, can give us the precise pi-phi correlations in terms of specific geometric ratios. And this finally corroborates the classical intimacy between these two triangles. As we have seen in last part of our video, if these two triangles are connected along their hypotenuse, common hypotenuse, their angles and their sides add up to reflect the precise value of golden ratio. And if we connect these two triangles along their longer catheters or along their shorter catheters, they provide us precise pi-phi correlation. This finally corroborates, this finally authenticates the classical geometric relationship between these two right triangles. So all these things, their details are provided in the paper, and the paper link is in video description. In this video, I have requested you so many times to please visit the paper link, because I know and you know this constant here, golden ratio, it is as important as pi. So this golden ratio must become the part of our curriculum. It must be taught in our school, colleges and universities. And our scientific calculators must have a button with this symbol, the symbol of golden ratio. So please visit the paper link and support my research work. Thanks for watching. Thanks a lot.